Hello folks, today we're going to be back with more multivariable calculus. We're going to do 3D space and vectors. We're going to be especially interested in vectors in three-dimensional space. So the first thing that we got to get right is how do we go from two-dimensional space to three-dimensional space, especially when we're talking about the axes. So here I draw the xy plane. We have the positive x-axis, the positive y-axis. I did not draw the negative ones. So when we're going to add another dimension, we're going to add the z-axis. The question is the z-axis going to come out of the paper or is it going to go into the paper, okay? So we got to make that decision, and that's a matter of definition. Luckily, folks that lived way before us, okay, have taken care of this. And there's a very easy rule. It's called the right-hand rule. What you do is, just look at this here. You point your fingers towards the positive x-axis, and you curl them towards the positive y-axis. Then your thumb always points towards the positive z-axis. Again, positive x-axis, curl them towards y, and it's always going to point towards the positive z-axis. Okay, so that's, in this case, that means it's gonna come out. The positive z-axis is going to come out of the paper. It's not going to go into the paper. It's going to come out of the paper. The way we usually draw them, the way you're usually going to see them in books, is you have the x here, you have the y here, they're in the plane, and if you curl from x towards y, again z is coming out like this, so that's the way you draw them, and it's 90 degrees or pi over 2 radians between every single axis. Okay, this is called the right-hand rule. So again, I draw it. You point towards x. You curl your hand towards y, and that's going to give you the z-axis. So in this case, z-axis is going to come out like this again out of the paper. Okay, so that's going to be our the way we're going to set things up. I want to go straight into vectors because that's going to take care of points also. So the way we're going to think about vectors is basically we're going to think of them like line segments. Okay, so what is a line segment? Well, a line segment starts from somewhere and it goes to somewhere. So we're going to think of them as line segments with an arrow, with a direction, okay? So for us, each vector is going to be an arrow. It's going to have a length and it's going to have a direction, okay? Usually, first when we start initially, they're always going to be, the tail is going to be at the origin, and then it's going to point towards a given point. So here I gave an example of a vector. When we think about it in terms of an arrow, if we're just on the xy plane, the vectors are going to be two-dimensional. For example, the vector -1, 2 would be, well, you would go to x-axis on -1, you would go to 2, so this would be the point -1, 2. Okay, when you have these angled brackets here, okay, that means it's an arrow. So what you do is you start from the origin and you draw an arrow to the point -1, 2. Okay, -1, 2. Now, with just the parentheses themselves is the point -1, 2. And if you draw the arrow, it becomes the angled brackets. That becomes the vector. Okay, so this would be, so the point and the vectors are two different things. Okay, the point is the point. The vector is starting from the origin. Its tail is at the origin. It goes to the point -1, 2, and you have these angled parentheses or brackets around it. Now, we usually, well, it's no surprise, we usually call a vector v. So good letters for a vector would be u, it would be v, it would be w. Sometimes you can use x, y, z. I, j, k are very good letters, but they represent the unit vectors as we're going to see later. Okay, so do not use a, b, c for vectors. Use u, v, w. That's much nicer. Now, to make sure that something we're talking about a vector, apart from this notation of these angled brackets, we're going to put an arrow on top of the letter v. Okay, so this is the vector v. When you see an arrow, you immediately know that we're talking about a vector. Now, in some books, there is no arrow, but the v itself is bold. It's very bold, okay? It's a very dark v, so that usually means that it's a vector. Now, we can represent this vector 1, 2, okay? 1, 2 another way, we can represent it minus I, minus 1 times I, 2 times j. This is just I is the unit vector in the x direction, and j is the unit vector these are unit vectors. This is in the x direction, this is in the y direction. Now, these were two-dimensional vectors. You might have seen them in middle school, you might have seen them in the high school, you might have seen them just right now. There's also three-dimensional ones. So let's consider a different vector v. This time it's going to be 2, 3, 1. Okay, 2, 3, 1. How would we draw this guy? Well, as you know, my drawing capabilities are very limited, kind of Picasso-like. So we were talking about 2, 3, 1. Again, I drew my positive axes. So 2 on the x-axis would be this point. 3 on the y-axis would be this point. So this point here, when I draw them like this, that would be 2, 3, 0. The z-coordinate is 0. So if I just raise it 1 up, it's going to be 2, 3, 1. Okay. So again, I'm going to put the tail at the origin, and I'm going to draw an arrow to this point. So it's basically going to be this vector here. Okay. It's going to be this vector here, pointing like this. Okay. So it's 2, 3, and the height is 1. Now, how can I write that in terms of the ijk notation? 2, 3, 1, I could do these angled brackets, or I could write 2i plus 3j plus k. Don't worry about the letters. These are just unit vectors. This is the unit vector in the positive x direction. This is the unit vector, unit meaning it has length 1. In the positive y direction, this is the unit vector in the positive z-axis. Okay. So we can also now talk about another thing. So we said these vectors are basically arrows, line segments. Okay. So an arrow has a length and it's got some direction it's pointing to. Okay. It's got a length and it's got some direction it's pointing to. So the next order of business is, well, from the coordinates, from the given coordinates of a vector, okay, we don't call these coordinates, we actually call them components. From the given components of a vector, how do we get its length and its direction? Okay, so those are the next questions that we're going to try to answer. Now here, if you read this while I was talking, sooner or later it's going to happen that we're going to get just tired of writing these arrows. So we're just going to drop the arrows, and you'll just know that we're talking about the vector because, you know, 2i plus 3j plus k, that's got to be a vector. It can't be anything else, okay? So sometimes today I'm going to pretty much try to do the arrows all the time. If I forget them, just excuse me. Later on, you're not going to write the arrows yourself either. So given a vector v with components v1, v2, v3, this is its x component, this is its y component, this is its z component. Okay. How would we find? Sorry, my bad. If this, let's say it's two-dimensional, it does not have any third component. Okay, my bad. Let's say it's just two-dimensional, so it's in the plane. It's in v1, v2. Okay, maybe it's 3, 2 or something like that. Well, the way you do it is you square the first component, you square the second real number, and you take the square root. That's just the Pythagorean rule. Why is that the Pythagorean rule? Again, if you could draw x and y, okay, y here. If this here is v1, and if this here is v2, okay, then the thing that we're talking about would be this guy. Well, what would be the length of this diagonal? It would be, just by the Pythagorean theorem, it would be just v1 squared. This would also be v2. So v1 squared plus v2 squared would be would give you the diagonal squared, or the length of the vector squared. So once you take the square root, you always are going to find the length of it. Okay. Now, how would we expand this formula when we're talking about three-dimensional vectors? So let's give ourselves a w. It's a three-dimensional. It lives in three-dimensional space. It's w1, w2, w3. The components are w1, w2, w3. Okay. So the way you do it is, again, you square all of them, you add them up, and take the square root. Okay. So it doesn't matter whether it's two-dimensional, three-dimensional. It doesn't matter if it's four-dimensional. You might have a hard time thinking about, well, what is a four-dimensional arrow? Okay. Well, you could have them 10-dimensional. That's why later on when you do linear algebra, you don't think about these vectors as arrows at all. You kind of think about them abstractly. But then we're going to do at most 3 dimensions right now. All you would do is square each component, add them up, and take the square root. So the formula doesn't change, okay? It does not change. It's just you keep squaring the components, adding them up, and taking the square root. Now here I try to explain why this would be so. So let's think about the vector 2, 3, 1, our previous example that we drew. Let's think about the vector 2, 3, 1. So here's the x-axis, here's the y-axis, the positive, here's the z-axis. So just 2, 3, 0 would be this point here, okay? So if I draw a vector in the plane, that would be the vector 2, 3. In other words, 2i plus 3j. It would be this vector. Well, how would I find its length? Its length would be 2 squared plus 3 squared in the square root. That's going to be square root of 13. Now, I'm not interested in the vector 2, 3, but I'm interested originally in the length of the vector 2, 3, 1. So how would I get 1? Well, I'm just going to go 1 up from the plane, okay? So this here, I'm going to draw the arrow. This one here would be w. Well, now we're going to apply the Pythagorean theorem again. We need the length of this. Luckily, we calculated this one, right? Square root 13. Now we need to calculate the length on the z. Well, that's just 1. So it's going to be square root of 13 squared plus 1. Well, guess what? That's just each, well, what was squared? It was square root of 13. Well, 13 was these guys squared, so it doesn't matter. It's the same way. Gives you the same answer both ways. So it's 2 squared plus 3 squared. That would give you 13. When you square 13 plus 1, which is the height here, okay? So this length, again, we're going to do the Pythagorean theorem, okay? It's not too bad. So these are the lengths. These are the lengths of these vectors. We can also, so far, every one of these vectors have been starting from the origin. Their tail is at the origin, and they are their head is at some other point. Okay. Now we can kind of give ourselves some flexibility here. What we can do is, well, we can take any 2 points. Let's say we take points P and Q. I gave the coordinates here for P, 1, minus 3, 2, and minus 1, minus 4, 0 is the point Q. Okay. And well, we can think about the vector whose tail is at P and whose head is at Q. Now, actually, vectors don't have any starting place, but I'm gonna later on, this is gonna be useful. We're gonna introduce starting places. If I just think about this as length and direction, well, how would I get this length? Well, one thing I can do is, if it's going to be from P to Q, I'll write PQ, P first Q, and then put an arrow on it to show that it's a vector, P to Q. If it was going to be from Q to P, I would write Q to P and put an arrow on it. Okay. What I'm going to do is, well, I need to subtract, take this x coordinate, subtract this one, take this y coordinate, subtract the minus 3, and take the z coordinate, subtract the 2. So where you end up minus where you start. So it's always, right, when you're trying to calculate these, it's always end minus start. Okay, end minus start. So we ended up at Q. It starts from P, goes to Q. So it's going to be minus 1, minus a 1. That's going to give me a minus 2 as a vector. Minus 4, minus a 3. So that's going to make it plus 3. That's going to give me minus 1. And 0, minus a 2. Okay, that's going to give me minus 2. So now if I'm trying to find the length here of this line segment here from P to Q, what I can do is I can just find the length of this vector, which is minus 2 squared plus minus 1 squared, 2 squared plus 1 squared basically, plus another 2 squared, so that's going to be 9. So the length of this line segment PQ, or this vector PQ, is actually just 3. Okay, so I wrote down the general formula for you guys here. It's going to be in whatever calculus book you're trying to follow. They're all going to have the same formula. In general, when you have the point P and the Q and point Q, and your vector starts from P and goes to Q, and the coordinates of P is x1, y1, z1. The coordinates of Q is x2, y2, z2. It's always end minus start. Okay, so x2 minus x1 is going to be the first component of PQ, y2 minus y1 is going to be the y component, and z2 minus z1 is going to be the z component. And the length itself is going to be just this guy squared plus this guy squared plus this guy squared, all in the square root. Now, there is actually one vector that has no length, that has zero length, and the only vector that has zero length is the zero vector. To differentiate, it's very important because we use the zero vector. So the zero vector is, well, it's got 0 in the x component, 0 in the y component, 0 in the j component. So you're basically just sitting at the origin. You're not going anywhere. The head is at the origin, the tail is at the origin, it's got 0 length. Okay? And I've said this before, but a vector of unit length is a unit vector is a vector of length 1. Okay? So this one here, v equals 0, 1, 0, which is basically the vector j, right? Because we said the y vector is y unit vector is j. Okay, so this would be a unit vector. Also, this guy would be a unit vector, w 1/2 squared 2 over 2. This would also be a unit vector. Why? If you square them, well, 1/2 squared plus 1/2 squared, 1/4 plus 1/4, that's going to be a half. Squared 2 over 2, so that's going to be 2/4, that's going to be another half. So the length of it is 1. So this is also a unit vector. Okay? So the unit vectors, the basic unit vectors that, the standard unit vectors that we want to talk about are, the standard ones are I, j, and k. This is the unit vector in the x-axis. This is the unit vector in the y-axis, and this is the unit vector in the positive z-axis direction. Now, what sort of cool things can we do with vectors? Okay, so vectors by themselves are certainly not that exciting, right? Okay, so we're not overfilled with joy here. So there's a couple of things you can do where there's basically two vector operations that we're going to talk about now. We're going to introduce another one. We're going to introduce actually two more very soon. The first one is we can add two vectors. Now, when I say add, addition and subtraction are basically the same thing. Basically, how it works is if you have a vector u and if you have a vector v, and let's say the components, the x component is u1. These are just real numbers. Don't let them scare you. So it could be 3, 1, minus 8 or something like that. So u1 is a real number, u2 is a real number, u3 is a real number, ditto for v's. Okay, these are the components. What happens when I add these vectors up? Well, you add each one of the components. You do u1 v1, that's going to be your x component. u2 v2, that's going to be your y component. And u3 v plus v3, that's going to be your z component. So you add them what we call component-wise. You do component-wise addition. Subtraction works the same thing. What you do is actually u minus v is the same thing as u plus minus v. I'm going to talk about what minus v means in a second. Basically, it's you subtract them component-wise. Again, u1 minus v1, u2 minus v2, u3 minus v3, that would be u minus v. Now, here I try to give you the geometric interpretations of adding a vector. So if you have this u vector, if you have this v vector, then you can just copy this v over here. So to the head of u, you attach the tail of v. So you had u here, and then you attach the tail of v. This is u, this is v. Then u plus v is going to be this vector here, u plus v. Okay. Now this is symmetric. If you draw this v and this v, this is going to be u also. So this is actually a parallelogram. Okay. So this diagonal over here would be just u plus v. Basically, so what it means is you add the tail of one vector to the head of the other to get the sum of two vectors. Okay, that's just the sum. Now, what about the difference? Okay, so here again, I try to draw a picture. It looks complicated, but let me just explain it. Again, I have u and v. Now, minus v means just flip your vector and go the opposite direction. Okay, so if v is going this way, minus v is going to be this way. So I copied u. Again, this would be a parallelogram. So here's minus v plus u. In other words, this would be the vector u minus v. But now just think about this. This side is going to be exactly this diagonal. So if you have two vectors, u, v, and if you start from the head of v and go to the head of u, you always get u minus v as a drawing. Let me say that again. You have two vectors, u, v. If you go from the head of v to the head of u, you get the vector u minus v. Why? Just stare at this for a second again. V, this would be minus v, add u to it, you get u minus v, which is this one, this diagonal. Well, it's going to be the same as this diagonal because they're exactly parallel. Okay? So addition and subtraction are pretty simple. You just do them component-wise. If you had to guess, that's probably the first thing you would have guessed anyways. Okay? The next thing we're going to do is scalar multiplication. Now, scalar multiplication, it sounds like a terribly scary thing. What is a scalar? What scalar is, in our case, scalar is just a real number. Okay, so basically what we're trying to do is we're trying to multiply a vector by a real number, by a constant. Say if we have v and we're interested in 2v. So if v is this vector here, I made a drawing, v is this tiny vector over here, 2v would be, I would add another v to v, to the head of it, I would add another v, so this would be 2v, minus v would be just flip it, minus 2v would be just take it like this, okay? So basically a scalar is just a constant. We're trying to multiply the vector with a constant. So if c is any real number, it doesn't matter whether it is positive. If it's positive, it's going to head in the same direction. If it's negative, it's going to head in the opposite direction. C times u is just going to be c times u1, c times u2, c times u3. So you multiply each component by the same number. Here I gave you guys an example. Here I gave you guys an example of scalar multiplication. 1, 2, minus 3, that's going to be our vector. What happens when you do 2 times it? It's going to be 2, 4, minus 6. What would happen if we did 1/2 it? It would be 1/2, 1, and minus 3/2, in other words, minus 1.5. Okay? What would happen if we did minus u? Well, I would multiply everything by a minus 1, so it would be minus 1, minus 2, and minus 3. I think I skipped this. I gave an example of adding 2 vectors as well. So we have this funky vector, 1, minus 2, 2, and we have 3, 1, minus 1. If I add them up, I would get 4. 2 minus 2 plus 1 is minus 1. 2 minus 1 is 1. So their addition is minus 1, 4 minus 1, 1. And subtraction, 1 minus 2, u minus v would be minus 2. Minus 2 and minus 1 would be minus 3. And 2 minus a minus 1 would be 3. So that's basically it. These are the two things you can do with them. Okay, so a vector addition is just adding the tail of one vector to the head of the other one. It's commutative, so it doesn't matter the order you do it in, it does not matter. Scalar multiplication is just taking a fixed copy, just multiplying the length of this vector in the direction it's heading if the scalar is positive, in the opposite direction if the scalar is negative. Now, why do we call the scalar? Why couldn't they say constant multiplication or something like that? There's a reason for it, okay? And the reason comes from general vector spaces. When you guys, if you've taken your linear algebra, you'll know about this, or you're going to know about it soon enough when you take linear algebra. Basically, not all vectors are over the real numbers, okay? Where the constants comes from real numbers. Some vectors are over complex numbers. There are other kinds of vectors, so it depends where the constants are coming. For us, the scalars are always going to be real numbers. We're not going to look at anything else. But because vectors could be just so much more general than arrows heading in some direction, the constants affecting those arrows can be a lot more general than the real numbers. So that's why it's called scalar. Scalar basically means just constant, okay? Just think about it that way. Don't let it scare you. For us, it's always going to be a real number. Okay, what's next? We're almost done here. What's next is we want to talk about properties of vector operations. Now, I wrote these algebraic properties. They look scary. I'm going to try to make them very simple for us. So we're going to take 3 vectors and 2 constants. These are going to be our real numbers, r and s. And the vectors are going to be u, v, and w. Oh my goodness, I forgot the arrows on top. My bad. Okay. So the first thing is u plus v. When you're adding 2 vectors, that's the same thing as v plus u. So vector addition is commutative. You can change the order. And it's associative, right? Adding u plus v plus w is the same thing as u plus v plus w. So that means you can drop the parentheses basically. It's exactly the same property of real numbers. u plus the 0 vector. Okay, so the 0 vector plus u is itself, okay? Because why is this? Because if you the coordinates of u1, u2, u3, the coordinates of 0 would be just 0, 0, 0, and you add them up again, you get u1, u2, u3. Okay, so u plus 0 is always u, and that's the same thing because it's commutative. That's the same thing as 0 plus u. Now u plus minus u is equal to 0. So if you multiply u by minus 1 and you add them up, you basically get the 0 vector. So this basically means they are inverses of each other in some sense. They cancel each other out. So if you go this way and then exactly go this way, you're back at the origin. That's all it says. Okay, it says something very simple. Now here, this 0 is a scalar 0. It's not the 0 vector. If you multiply any vector by the number 0, you get the 0 vector back. Why? Because if your u is equal to u1, u2, u3, right? If I multiply every single one of those coordinates by the number 0, I'm just going to get 0, 0, 0, which is the 0 vector. Finally, it's not finally, 1 times a vector, multiplying by a vector just gives itself back. Then we come to scalar multiplication. So you have a constant r, you have a constant s. So if you do this multiplication first, then you do this multiplication, it doesn't matter. It's just, it's always going to give you r times s times u. So you can drop the parentheses. Now, how does scalar multiplication distribute over vector addition? If you do r times u plus v is a vector. If you do r times it, that's the same thing as doing r times u plus r times v. And again, we can talk about adding two numbers and then multiplying it by a vector. That would be r times u times s times u. Okay, so these are, you don't have to really memorize them. If you had to make a guess, this would be just the right guess. Maybe you don't know how to do it, but if you worked out every single example, you would make these guesses. These are the natural ways to do vectors. Vectors are very intuitive in some sense. Now, I already talked about the unit vectors. The standard unit vectors are I, j, k. I is 1, 0, 0. J is 0, 1, 0. K is 0, 0, 1. So any given vector with components v1, v2, v3, I can write them as v1 times I plus v2 times j and v3 times k. Okay, I can write them like this. Now, if you've noticed, so far, the only thing that we've been talking about is basically the length. Okay, what about the direction of a vector? So I have a vector like this. Okay, it's got this length and it's got this direction. Now, let me take the cap off. Look at these two vectors side by side. They've got different lengths, but they're heading in exactly the same direction. So somehow we're supposed to be able to say what direction a vector is going in. Now, if we were in two space, if we were on the xy axis, that would be very easy. We could say east, west, so many degrees east, so many degrees north, whatever. Okay, we could say right 30 degrees east of north or something like that. It would be very easy to do in two space. When you're in three space, these guys are really funky, right? They can go any which direction they want. So the way we're going to talk about direction is the following. Given a vector, I can do something really, really weird. I can divide the vector by its length and multiply it again. So these basically cancel each other out. V times length of v, this is length of v, cancels out with length of v. Well, then you just get the vector v itself. Okay? So now, this here is the length. This vector has unit length, right? Because I've divided this vector by its length. So now this vector here has unit length. So it's the unit vector in the direction of the vector v. So that's how we determine direction. So if this cap has length 1, okay, and this was my vector, to determine direction, I would just give you the unit direction of the unit vector going in the same direction. Okay, I would just give you guys the unit vector going in the same direction. Now the formula looks a little scary. There's nothing to be scared of. Let's say I have the vector 2, minus 1, 2. And I'm interested in which direction it's heading. Well, the first thing I got to do immediately is I got to calculate this length, square each of the components, add them up, then take the square root. That's going to be 3. So now divide each of these components by the length. So write v as 3 times v over 3. The 3's cancel basically. So v over 3, then what we're talking about is v over 3 is going to be 2/3 minus 1/3 2/3. In other words, it's going to be 2/3 I minus 1/3 j plus 2/3 k, okay? So this would be a unit vector heading in the direction of this same vector. If you don't believe me, as an exercise, please find the length of this vector. What's it going to be? 4/9 plus 1/9. That's going to be 5/9 plus another 4/9 when you square this. So that's 9/9. So its length is really 1. Okay, so this is a unit vector heading exactly in the same direction of this guy. Okay, so that's what we mean by direction of a vector. With the direction of a vector, or we determine it by finding the unit vector heading exactly in the same direction. We're going to see many applications of these. Don't worry if it seems like a lot of formulas at the same time. Your book is going to have them in nice big boxes anyhow, but you're going to use these formulas so many times that you're not going to even have to memorize them. You already know most of them anyways. Finally, most books have the midpoint of a line segment. So if we have a point P with coordinates x1, y1, z1, and if we have a point Q with coordinates x2, y2, z2, okay, the way we find the midpoint M is we just add x1 plus x2 divided by 2, y1 plus y2 divided by 2, z1 plus z2 divided by 2. In other words, I'm finding the average of the x coordinates. I'm also finding the average of y coordinates. Remember, the average of two numbers is you add them up and divide them by 2. And the average of the z components. Well, that makes perfect sense, but why is it that way? So here I drew it for you guys. We have P and Q, so I want to find this midpoint M, okay? So, well, what do I know? Here, if I look at the vector OM, right, that's going to start from the origin. It's going to end up at M. Well, what is that equal to? That's equal to the vector OP plus PM. Okay, OP plus PM. But since M is the midpoint, PM is the same thing as PQ divided by 2. It's just 1/2 PQ. So you have OP plus 1/2 PQ. So what is OP? Well, OP is just the coordinates of this point, right? x1, y1, z1 as a vector. And what is PQ? Well, half of PQ would be x2 minus x1, y2 minus y1, and z2 minus z1. 1/2 it would be just divided by 2. Now when I'm adding them, there's something very nice. Here is x2. There's going to be a minus 1/2 x1. There's a x1, so it's going to, at the end of the day, it's going to be half x1. So it's going to be 1/2 x2, half x1. So x2 plus x1 over 2. y2 plus y1. Same thing for the second coordinate. Same thing for the third coordinate. So you don't need to know this proof. What you need to know is the formula for it. So basically, you're taking the average of the components and writing them component-wise. Now, that's all I want to do for this section. Later on, we're going to introduce, hopefully next class, we're going to introduce the dot product and the cross product. And till then, take care. Bye-bye.